So today the goal of getting into Chapter 4 is to introduce us to a really important topic. I think one of the ways that as a student you guys can, sort of understand, when something is really important is to look at your syllabus and see, how long that topic is on your syllabus for. We took 2 days for Chapter 2, 2 days for Chapter 3, setting aside 4 days of our work for Chapter 4, right? So it's a pretty significant topic. It doesn't make it harder, all right? Don't misunderstand importance and degree of difficulty, right? There are some really important, I hope you would acknowledge, basic concepts that you learned to get to this point that more time was spent on, that now you realize, oh, that wasn't the hardest thing in the world. You just really needed to have a solid understanding of it. And the concepts of symmetry and group theory, which is what we're going to be covering in Chapter 4, fall into that category of being particularly important, right? Symmetry, of course, is a word that everybody's heard. We were looking at symmetry last class to help us decide whether a molecule is polar or nonpolar. But today we're going to be looking at additional attributes of what symmetry is. Group theory is an expression that describes a mathematical approach. That's really what it is. And in group theory, what we'll see through today's class and through the next couple of classes is that rather than having to treat every molecule individually, every time we're asked to think about a molecule individually, all right, if we can put it into a group, a class of other molecules that are just like it, we will understand its behavior based on how that entire class behaves. All right, so it's a really powerful tool. All right, and what we really need to do then is understand what are those classes, what are those groups, and everything. Okay, and all those groups are dictated by the symmetries that are present. Okay. And so I'm going to bring the projector up in a minute because the drawings, the illustrations, I can project some of the artwork from the textbook, are just going to be a lot easier, cleaner to see than to have me trying to draw them. And I brought in a couple of models today as well to try to help us visualize. All right? Visualizing is really important for this work. And so if you have a model kit from when you took organic, it might be helpful to find it and break it back out here in the next chapter or two, because we'll use group theory again in a couple of chapters, a couple additional chapters. We'll use it. Okay. So there are two things that get a little bit mixed up. So let's talk about what a symmetry element is, all right, versus a symmetry operation. Okay. An element, and if this was a grammar class, we would say that an element is like a noun, and the operation is a verb. That's one way to think about the difference between these two. Okay. A symmetry element is a physical attribute of a molecule. Related to symmetry. The main symmetry elements that exist are something called identity, all right? Then there is rotation, reflection, inversion, and improper rotation, or sometimes known as rotation dash reflection. So these are elements that a molecule possesses. Okay? For example, well, the elements actually would be, I guess I kind of did, these are the actions down here the element that's associated with rotation is an axis. Okay, that's going to be the noun. The element associated with reflection is a plane, a mirror plane. The symmetry element associated with inversion is a point in space. And improper rotation, again, would be an axis. All right. Identity is just the entire molecule. It's not really an element associated with that. So this molecule that I have here, which, without anything on the ends, could be a variety of things. It look a little better against the white screen, so I'll hold it up like that. Is possessing several symmetry elements right now. One of which is an axis. I could rotate this molecule 180 degrees, and it looks exactly the same, right? So that's what these elements are. The operation then is the act of performing, okay, an action on a molecule to determine if it changes the way we see the molecule. Okay. So now that's kind of unofficial, the way we see the molecule. Okay. So let me demonstrate what I mean by that. Okay. So right now, again, if I take this and I do that same thing that I did earlier, I rotate it. If you had taken a picture before and a picture after, it looks identical, right? So this molecule is symmetric about an axis that goes right down through the carbon-carbon double bond, right? So that's called an axis of rotation, okay? This molecule is also in possession of a plane, a mirror plane, that comes right down the molecule as well. If I were to pretend that this was a piece of paper and fold it, right, the two sides would line up perfectly with one another. Or if I reflected this side over to that side, okay, and the right side, as you're looking at it, back over to the left, it would still look the same, exactly the same. Okay? Now, there is the potential for there to be an axis through the molecule this way. But if I spin the molecule that way, it now looks different. Okay? And if you overlaid the picture that you take right now on top of the other one, the red balls would not line up with where they were before. So that is not an axis of rotation, nor is it a mirror plane either, because these atoms are different from these atoms here. Okay? So these are the basic ideas of symmetry elements. They can be these axes, these planes, what's called a point of rotation, or inversion, center of inversion, and then I'll show you improper ones as well. And then the act of trying these things to see if it leaves the molecule unchanged would actually be rotation, reflection, inversion, improper rotation. Okay? So let's pull up some pictures and look at some of the symmetry elements that are typically present in molecules. Right? So now every molecule is going to possesses the identity element and operation. So this is just present for mathematical completeness. Okay, which might not mean a whole lot to you right now. When we start to look at the what are known as the character tables, we'll see that they need to be square and one of the only ways to get them to be square is if this operation is present. So every molecule possesses itself, in other words. Okay? If you just leave it alone, don't do anything to it, the before and after pictures are identical. So that is a slight degree of symmetry. Okay? Not doing anything to the molecule. All right? Now, the next, in terms of sort of categorizing the next important ones, the axes of rotation are sort of the next thing that we often look for in a molecule. So here's several examples from nature. Okay, let's start with the snowflakes actually here. There are several different axes of rotation about this snowflake. From this point to this point is a C2 axis. We could rotate the molecule 180 degrees. All right. Now what the 2 means when we talk about an axis of rotation, C is always the label for an axis of rotation, and then the subscript N is associated with it. N is equal to 360 divided by the degrees of rotation for the symmetry element. So in the case of that snowflake, or in the case of this molecule that I had earlier, I rotated it 180 degrees, right? So 360 divided by 180 degrees is 2. So that implies a C2 axis. Okay? A C2 axis. Right? The molecule also has a C3 axis. The C3 axis is coming out of the board, or out of the projector, out of the screen, right towards you. If you're looking down on this and you rotate it this way 120 degrees, you'll bring that point onto what was another point just like it. All right? And so it's 360 divided by that 120 degrees rotation is a C3 axis. Okay? This also possesses a C6 because of where the points are. So you can rotate it just 60 degrees again through the center point there. All right? And that would be a C6 axis that it has. All right? Molecules like a chloroform here, right? All right? Have a C3 axis. If we look down on the chloroform from above, I can quickly build one for us to show this to us. Okay. If we're looking at a molecule this way, we may not see it. But again, if we look at our chloroform from the top, from the hydrogen down through, now it looks like a three-sided, like a triangle, right? The base of it does. And you can rotate it 120 degrees, and it looks exactly the way that it was before. All right. And this is where visualization tools, sketches, a molecule kit are really going to be helpful to have you allow you to see all of the elements of symmetry that might be present. Okay. This guy right here has some sort of high-level axis here. All right, so it's, how many, the other way to think about what the N is how many parts you divided a circle into, right? So with C2, you've divided your circle into 2 parts. All right, C3, you divide a circle into 3 parts. So you could count here this circle, if you called one of these the axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a C10 axis in that structure right there. All right, and so that's a 36 degree. And if we work backwards, right, 360 divided by the 10 gives us 36 degrees of rotation, brings each atom to the position of where another atom was before the rotation there. Okay, so we look for these axes of rotation. Okay. All right. I don't think the advanced. Oh, it is working. Good. All right. So now we've got some mirror planes. This is the next concept in symmetry, are mirror planes. A person, generally speaking, possesses a mirror plane, all right? Right down through the middle of your body, your left side could be reflected to your right side, and it's essentially the same thing, all right? Each point, if you're symmetric, each point on the left side would end up in an identical point on the right side, all right? So there's no n associated with a mirror plane. Mirror planes are given the label sigma. Okay, sigma, Greek letter S, sigma. Okay, there are going to be a couple of different categories of mirror planes, as we'll see, which causes a few headaches here. There are sigma V's, sigma H's, and sigma D's. A sigma V, the V means vertical. This is a mirror plane that contains what's known as the principal CN axis. So this pencil has a C6 axis going right down through it. If you have a traditional pencil, all right, it's a hexagon, right? And so that's why it has a C6 axis. You can rotate it 60 degrees right down the shaft of the pencil, and you bring each corner onto another corner. All right. There's a mirror plane that goes right down through that axis. Actually, there are 3 different ones. And so these are the 3 sigma V's of a pencil. A sigma H is a horizontal mirror plane. This is going to be perpendicular to the principal CN. The principal means the highest n value. So if an object had a C2, a C3, and a C6, like a snowflake, the C6 is considered the principal axis. The higher you can go in n, the more important you are in the thinking, in the logic that we're going to see of group theory. Okay? And then sigma D, D means dihedral, but perhaps an easier way to think about it is it sort of is diagonal. Okay? It's going to be between, okay, other axes and planes. And they're often the trickiest ones to visualize. Luckily, this is another than the power of group theory. We won't always have to know that they're there. We can use some other techniques to figure out what group a molecule is in, and then we already know what all the elements are of all the groups. So that's, again, part of the importance of this philosophy that we're going to look at here. Okay? All right. The next element is a center of inversion. A center of inversion would take everything, squeeze it through a central point, and push it out in 180 degrees to the other direction. Okay? So if I had a point up here in a molecule, it would come through the center of inversion and come out the other side. If it ended up on where an atom, just like it was in the original molecule, it would contain a center of inversion. If I go back to my flat molecule that I had earlier, okay, take away the reds, this has a center of inversion. Because if I take this exterior atom here, push it through the central point, the center of gravity, so to speak, of the molecule, it would come out on where another atom was. Same thing here to here. Okay? So there's a center of inversion. This atom goes through to this atom over here. All right? So this is, a trickier one to see here. This molecule, this is an interesting case here. They're showing you how center of inversion works for, this is the staggered form of ethane. So ethane has a center of inversion in its staggered conformation, but not in its eclipsed conformation. Because in its eclipsed conformation, this wouldn't be flat in the plane with H6, right? The 2 and 3 would be at the bottom. And so when the 6 comes through, it would be in the plane where 1 is, so it would not line up. So depending on what conformation, which is the actual like rotation of a bond, all right? Depending on where the molecule's at one moment, it may possess different elements of symmetry, okay? Which it lends to more confusion here. Of course, this is the tetrahedral arrangement in methane, and it does not possess a center of inversion either. All right, these are just some shapes that have symmetry. Let's get through. Okay, the last real symmetry element is the rotation reflection, or improper rotation. Rotation reflection is two actions. You rotate according to the n in the rotation label. So since I've given you some of the others. Oh, the symbol for inversion, by the way, is I. We say I is the sort of the label for labeling something as having a center of inversion. Again, and then the last one is called an improper rotation, or rotation reflection. It's given the symbol S and a subscript of N. So in an improper rotation, you rotate, okay, the molecule on a Cn axis, so whatever the n value is. Then you reflect through a sigma h, a perpendicular thing. Okay? So you would take your molecule, if you were thinking it had an S2, you would rotate it 180 degrees, and then you would reflect the bottom to the top. This would be an S2. Okay? All right. So that's how that would work. Methane has an S4. Okay? It doesn't have a C4 axis. All right? Interestingly. So the Cn isn't necessarily an actual proper rotation axis in the molecule. But in methane, this is showing us in a box here. They've drawn a cube, all right, to help you keep track of the corners. It's a pretty clever way, I think, to do it. And notice how all the hydrogens are labeled. So if we take our cube and we rotate it by 90 degrees, it's going to bring this front left over to the front right. Okay? And then if we conduct a mirror plane, swap it, it would drop down to the bottom. It was at the bottom, would drop to the top. And you can see we now have 4 hydrogens in exactly the same spots. Okay? So that is an improper rotation that brought the molecule back to exactly the same configuration. All right? If one of those hydrogens were switched out for a chlorine, this would go away. All right? Because then the chlorine would not end up in the original spot that it was in. Okay? This is just showing you that upon performing a second one, you still arrive back at another the equivalent structure again. Okay? So that's an improper rotation that we have. Okay? So if we look at some molecules here, like the water molecule, there are a lot of symmetry, well, not a lot, a few symmetry elements present in water. Okay? So water, and I could just use the little, take one of my things off here. Okay? Water possesses a C2 going right down through the oxygen. Okay? So it would come right down through here. Okay? And you could turn the molecule 180 degrees on that. Okay? It also possesses a sigma V. We can reflect this side to there, and that, the right to the left to the right, and we end up with the same thing. Okay? It does not possess a center of inversion. It does not possess a horizontal mirror plane. Nothing perpendicular to that C2 axis that we had. All right. So those are really the elements, and it possesses the identity element. Everything possesses the identity element as well. Okay. All right. Any other thoughts or questions on water and what it has or doesn't have? Yeah.
What do you mean by inversion point?
Okay. So this inversion point, again, would be a point through which every atom is moved and, I guess you'd say, pushed to an equal distance on the opposite side. So if we had a figure that looked like this, okay, and we don't have to just do this for molecules, all right? If we had a figure that looked like this, even though it's not an actual physical point in the molecule, this would be a center of inversion, because I could push this atom that distance through and then that distance on the other side. Right? So how far it is from the center, push it in the opposite direction through the center. And every atom would do that. It would end up where another atom is, and so we would say it has a center of inversion. Did that make clear to you then? Okay. All right. The key is however far you are, you come through a singular point, every atom, and then if you just keep going from the, along the vector from which you came, now an equal distance, again, the distance that you came, go that far again. If you end up where an atom was before, then you have a center of inversion. If every atom ends up where that was, okay? This would not be true if we changed this shape to well, it's easier to draw a triangle. If we tried to do this for a triangle, and I brought this down, right, my triangle is going to invert and look like that through what I thought might have been a center of inversion, okay? So this does not possess a center of inversion, all right, because it doesn't draw me the exact same shape again. Okay. Questions on any of the other elements before we continue looking for them here? Because being able to define these helps you identify what group a molecule is in. Okay? All right, so we have here a dichlorobenzene, okay, para-dichlorobenzene, right? So what elements are in this molecule here? There is, and this is where you have to start visualizing not just stuff being on a flat piece of paper. All right? It can fool you seeing a molecule being written flat like this. Although this is a planar molecule, right? There is an axis of rotation that comes right down through here. I could rotate it 180 degrees. Again, so here's a chlorine. I can spin that molecule 180 degrees, and it ends up looking just like it did. Okay? But there's also an axis of rotation through the two chlorines. I can spin the molecule 180 degrees this way. Okay? And there's an axis of rotation right through the center. I can rotate the molecule 180 degrees that way. So there are three different C2 axes on this molecule available. Okay? Neither one is, higher priority in this case, all right? But and then there are also some mirror planes in this molecule. Each of the axes has a vertical mirror plane through it. All right. The axis itself, if you made it like a plane of glass, you could reflect each side through it. The plane of the molecule is also a mirror plane. So not only does this have the axis of rotation and the vertical mirror planes, but there's also horizontal mirror planes. Okay? A horizontal mirror plane, let's stick with the easy axis of rotation coming down through the molecule this way. A horizontal mirror plane would be coming out like this. The top part of the molecule would reflect onto the bottom part of the molecule. Okay? This has a center of inversion, okay? Because every atom is across an equidistant from another one. Okay, this is, increasing amount of symmetry in this molecule here. Right? So there's a fair number of symmetry elements that are present in this molecule.
What was the last one you said it
It
had?
has center of inversion. The last one we can recognize as the center of inversion. Okay. What we need to be able to visualize the most are the axes, the principal axis of rotation, the C's, not the improper ones quite so much, and then the mirror planes, and sometimes the inversion. Usually the S is not required for us to be able to identify the point group that a molecule is in. All right. Here again is ethane in its staggered form. Okay. We'll go back to that, and we'll look at some of the symmetry elements of ethane in its staggered form. This has now a C3. Perhaps I could build ethane in a staggered conformation for us real quick. Okay. So I've built ethane in its staggered conformation, so we can see that we have the one, as you're facing you, hydrogen in the up position, and in the hydrogen that's facing me is in the down position. All right. So that is the staggered conformation. Now this molecule has a C2 axis right through the molecule. I can rotate it 180 degrees that way, and look, okay, now as you're looking at it on the left, there's a lone hydrogen up and a lone hydrogen down, right? And if I rotate 180 degrees, it's still lone hydrogen up on the left, lone hydrogen down on the right, okay? And so that's got a C2 axis that way. It doesn't have a C2 axis this dimension, so that, let's call it, if we call that like the Y dimension, okay? It does not have a C2 in the X or in the Z. If I rotate it in the Z direction, the lone hydrogen on the upper left now lies on the right. So it's not the same. Okay? And if I try to rotate it 180 degrees in the X direction, the lone hydrogen that was on the upper left is now on the bottom. Okay? So it's only got this one coming that direction. It does have a C3 down what we thought of earlier as the X direction though, right? We can rotate it 120 degrees and we're right back to where we were each time. Okay? 120 degrees, not 60, because that circle is divided into 3 parts, as you can see there. Okay? So it's got a C3 axis. It has a center of inversion. From here down through the center of the carbon-carbon bond would bring this hydrogen down to here. Okay? Any one of these. The back upper right would come through and become the bottom front left. Okay, so there's a center of inversion. It, let's see, what about mirror planes? Does it have any mirror planes? The only mirror plane it has is down the molecule this way. So the way you're looking at it, the front can be reflected onto the back, because these two atoms would reflect onto each other. Okay? And then the two on the right side would reflect onto each other. All right. So those are some of the symmetry elements of this. If we change this to the eclipsed conformation, we've completely changed the symmetry that it possesses now. All right. It no longer has that 180C2 that we originally had, because this was up here. It doesn't end up on, there was no atom down here, right? There's nothing left up here where it was. Okay. It still has the C3, okay, and now it has more mirror planes. Now it has mirror planes that are horizontal, okay, in addition to the vertical mirror plane, and it's lost its center of inversion. Okay, yes?
The one thing I guess I'm not understanding is how you tell the difference between the vertical and horizontal mirror.
Okay, yeah, it's tricky. So once you establish the highest value of n for rotation, so for this case, C3, everyone has to kind of come into what's the best visualization tool for them. For me, it would be to reorient this molecule so that that CN axis is vertical, right? Because V means vertical, and so I'm going to use that as a visualization tool. It doesn't have to be that way. But so now this molecule is vertical. There's a mirror plane that possesses, that's part of that axis, in other words. Okay? A horizontal mirror plane then would be perpendicular. So the C3 is going down through the carbon-carbon bond right now. A horizontal mirror plane would be this, where my hand is right now. And if you reflect the top through to the bottom, it lines up the same. The vertical mirror plane, though, I can reflect the left to the right as you're looking at it, and it ends up on itself. Okay, so it contains the CN axis. Yes?
So is there an example for like
The diagonal ones? Not in this molecule right here. I don't think so. Well, there might be, actually. In one of its conformations, I think it has a diagonal mirror plane through here. Like this, they're tricky, okay? Through here, you can reflect and you'd end up getting it back. So they're the sneakiest ones to see, okay? All right. So, flowchart. Big, fancy flowchart here. It's going to be a very important flowchart. You won't have to memorize this flowchart. Don't worry about that. That's not what we're doing. I will provide this for you when you need to use it on exams and quiz and stuff. And it's in the book for you, to use. Okay. This flowchart is used to assign a molecule to its point group. The term point group refers to, I guess that doesn't fit there the way I thought it did. Okay. The term point group refers to the mathematical grouping of all molecules that possess the same set of symmetry elements. All right, and that's called a point group. So if we decide that water is like some other molecule, that they share the same symmetry elements, they're part of a group or a class, and we call that a point group. In the case of water, it's going to be called the C2V point group, as we'll see. So let's work our way through what this chart tells us to do. I hope you can read this. It's the only way it fits all on the screen here. At the start, these questions will almost always be no's, the first couple of ones here, because there are some highly unsymmetric molecules, or what we call low symmetry molecules, that are just what we call C1, C3, it looks like, and CI. We'll show you some examples of those. All right. So they're unique. They're pretty rare, to be honest. You won't encounter them. Like I said, usually you're just going to ignore this first two steps. There are also some molecules of very high symmetry. The tetrahedral and the octahedral are two of the more common cases. So like a methane actually is a highly symmetric molecule, as it turns out, right? And then the octahedral molecule, so if you think about like sulfur hexafluoride, it's highly symmetric, right? So those may be some of the common examples in that category, all right? But we're usually going to not be interested in those really low or really high. We're going to look at a bunch of molecules as we're learning this that we need to use the bulk of this. Okay? So what you'll do for most molecules is you'll be starting here. You'll be looking for the highest order rotation axis. So the highest C. C2, C3, C4, C6, C5. They can be, anything. Okay? So you identify that. Then it's asking you the question, is there a perpendicular CN to that? Perpendicular C2, actually, not just CN. Is there a perpendicular C2 to that? So if I come back to my molecule I had here, my ethene molecule, right? And if I had said, oh, okay, this is the C2 axis going down through the molecule, and it rotated 180 degrees. So now it's saying, is there, perpendicular to that vertical line, is there another C2? And there is. There's there is. I can rotate it that way, and actually there's one this way. There's two perpendicular C2s. Okay? There's actually a little rule that says if you can find one perpendicular, you can find n perpendicular. So if you found that you had a C3 axis and you can identify one perpendicular C2, there are actually three perpendicular C2s to be found. If you find a C4 axis and then identify a perpendicular C2, there are four perpendicular C2s to be found. You don't have to find all of them to continue the work in the flowchart, but that's how many really do exist. All right? And we'll see that when we look at some of the point groups later on. So, if you identify a perpendicular axis, as I did for this molecule, you move over here to the left side. Everything that fits into that category of having perpendiculars, the point groups are labeled D. All right? They're going to be D something. All right? So then the next question is, do you see any horizontal mirror planes? So again, sticking with this molecule, this is my principal axis here. So a horizontal mirror plane would be perpendicular to that primary axis here. And yes, this does contain that horizontal mirror plane. So if I say yes, this molecule is now labeled as part of the D, and you use the N that was your highest order axis. So I would, yeah, see it says Cn here, but the highest order is going to define what N is the whole way through. So this molecule is part of the D2H point group. Okay? If it did not possess a horizontal mirror plane, then you would look for a dihedral mirror plane. Okay? So it's some sort of diagonal. If it possessed it, it would be D2D or DND. And if it did not possess any of those mirror planes, it would be DN, so D2 or D3. Okay? That's a pretty rare one. I doubt you end up there too often. Okay? That's sort of a little out of the way corner. All right? Okay? Definitely going to see DNH and maybe a couple of D2Ds or DNDs. Okay? D and D. All right. All right. So now, back up here. If our molecule did not have its perpendicular C2, okay? So let me go back to this would be like ammonia, okay? So this is essentially the ammonia molecule. The red will be the hydrogen in this case instead of thinking of it as white, okay? Well, actually, I'll just make the red different, okay? So these are hydrogens, okay? So this molecule has a C3 axis right down the bond or whatever this is between the red and the center, right? You can rotate it 120 degrees and it comes back to looking like itself, all right? Can't find anything higher than that. Can't rotate it 90 degrees or 60 degrees, okay, to get a C6 or something like that. So C3. So is there a perpendicular to that? Is there a way that I could rotate the molecule and bring it back? No, there's not in this case. So we're over here on the side where all the groups are going to be C or S groups. Okay? So the next thing we look for is, again, a horizontal mirror plane. Again, this helps to orient your molecule so that your Cn axis is pointing up and down. And then you're looking for anything perpendicular, horizontal to that. That's not present because then I would be reflecting the red down to the bottom. Okay? So if there's no horizontal mirror plane, you keep following down here. You look for a vertical mirror plane. Yes, this actually has three vertical mirror planes. Each one of these sort of triangles that I could make here of the red atom, the central atom, and one of the open ends defines a plane about which you could reflect the two sides of the molecule. All right? So yes, so this is then going to be called C. Our axis was a 3, right? So C3V is what this molecule is called. All right? If we had said no to the mirror plane, we then would look for an S. This is saying 2N. So if N was 3, we'd be looking for an S6. So can you rotate it 60 degrees and then reflect it? All right? It's going to be that's going to be more difficult to find, but you know, if you've gotten down here, you know, it's a pretty good bet you know exactly what you're looking for then. And then whether it's yes or no, it would be called S. So if n was 3, it'd be S6, and if it wasn't there, then it would just be called C3. Come back up here. If you did have a horizontal mirror plane, you end in CNH, so C3H is in the case of if we'd had a C3 there. Okay, so that's how you follow through. There are slightly different variations on this assignment flowchart in different books. Like a PChem book may have a slightly different way of asking the questions. All right, but these are the groups, and you're going to end up in these same in the groups, regardless of which assignment one you're using. Okay, so don't be alarmed when you go on and take PChem, or if you have seen a different version of this. Okay, because that's perfectly fine. Okay, let's look at some molecules here and see if we can start to assign what the symmetry is to some of them. Any questions on any of it so far, by the way? Or you okay? All right. Okay. All right. I'm going to write up some of these. I'll pick a few of these here, and then we will go ahead and go back to the assignment chart so that we can work through it together. Okay. So if we pick one of these molecules, the HCl, we're going to see is going to be one of the low symmetry molecules. Okay. Let's look at the PF5. That's an interesting one. Okay. How about we already did essentially NH3. Let's see about so that's PF5. How about the H2O2, hydrogen peroxide? And what's another interesting one there? We actually kind of looked at the ethane already. I think okay, we'll look at this 1,5 dibromo. Look at these. Okay. All right. So whether or not a molecule is of high or low symmetry, we kind of need to know what those high or low symmetry groups are. The high and low symmetry groups are defined in two tables in your textbook. So if a molecule presents itself to you and you think it looks abnormally symmetric, like there's a lot of stuff going on, you might consult that, or if it looks like there's really nothing there. One of the things that's really important, though, is what's known as an infinity axis. This is a C infinity axis. I can rotate an HCl molecule any degree that I want, write down its HCl bond, and it's identical to what it was before. Do you get that? Essentially, it's like my piece of chalk right here. It's a straight line. I can rotate it however many degrees I want, and it looks identical. Okay? So that is what's known as an infinity axis. As soon as you recognize that, and carbon dioxide was one of the other examples that would possess this as well, it's immediately in a group of high symmetry. Infinity, right? It's a big number, right? So just remember that. That's why it's high symmetry here. But that's the only thing that it possesses, okay? And so one of the groups is known as C infinity V. It's a linear molecule, infinite rotations, okay? And infinite reflection plane containing the rotation. So the other thing that this has, and this is kind of, students could think this is kind of hinky, right? But there's an axis, right, going down through my chalk here. There's also a vertical plane. The right half of the hydrogen atom would get reflected onto the left half of the hydrogen atom. The right half of the chlorine onto the left half of the chlorine, right? And those are going through that vertical axis if we orient the molecule that way. All right? So that's where the V comes from in this C infinity V. Okay? If we threw in our carbon dioxide, all right, to show you what the difference is there with carbon dioxide, it has a C infinity axis as well. However, it additionally has a horizontal, it's got a C2 axis that goes this way as well. All right. And then it would have horizontal and vertical mirror planes, and it has a center of inversion to it. So there's a fair amount of symmetry in a carbon dioxide molecule, and it's a special group called D infinity H. We're going to give away for both of those that infinity axis. And so as soon as you see an infinity axis, you'd want to look at the 5 possible high symmetry groups, only 2 of which have infinity axes, so it's immediately going to be in one of those 2 groups. Okay, so that makes life a little bit easier for that. Okay. All right, PF5. All right, the reason we're doing this chapter after the last chapter is because we need to know the shapes of molecules. So PF5 is the trigonal bipyramidal molecule, or shape, right? So there are some different axes present here. There is a C2 axis right there. Okay? This whole molecule could be rotated. It goes through one of the fluorines, between the 2 fluorines that are out of the plane, and when we rotate it, they flip over onto each other that way. Top and the bottom flip. But that is lower in priority than the axis that comes right down through the axial, as we call them, fluorines. That is a C3 axis there. Okay. So now, can we find anything higher? C4. Is there any way we could rotate this molecule 90 degrees? No. If you rotate it at 90 degrees, your axial ones would end up in the plane here. You'd have 2, no longer 3 in the plane that we have right now. Okay? So you're done at 3. So we're not in a high or low symmetry group here. Okay? Our highest order of axis of rotation is C3. So do we have perpendicular C2s? Yeah, I've already identified it. Right? So there's one. Actually, each of the fluorine phosphorus in this plane is one of those C3s. That's why I said there are 3. I know that there are going to be 3 C2s perpendicular to our C3 axis here. Okay? So we have C3 as the highest. We do have perpendicular C2s. Check. Okay? So that moves us over to the D side. Is there a horizontal mirror plane? Horizontal would be, again, a plane perpendicular to this highest axis of rotation. So yeah, the fluorines that are equatorial to the phosphorus, with the phosphorus, that's a reflection plane, because then this fluorine would reflect onto this fluorine here. So we do have a sigma H. Check. Right? So that tells us that we are in the D3H point group then. Right? As we answer yes, we just use D, whatever our N value was, and the H is designated there. So the only variable is what you found N to be. Right? Any questions? This is the first time most of you are seeing this, right? This is the first time most of you are ever doing it before? Yeah. No? Yes? Yeah? Okay. Okay. So it would totally be fine if you had questions. Okay? It really would be, Fine. Okay. All right. What do we have? Let's see what our next one is. H2O2. And the way we had it written, right? Okay, it's like this. You want to remember that H2O2 is planar, right? It's flat. Okay, that's the way it's going to be. So you start looking for axes of rotation. It's so tempting to always think about the bonds as being axes of rotations, okay? Because they're elements that you see, right? So this, I'm tempted to think, okay, well that's not an axis of rotation, right? Because then this hydrogen would flip down there, okay? And then, what if we drew a vertical line this way and tried to rotate it? Well, this hydrogen would end up over here, not where it is right now, okay? But this is, okay? So I'm going to draw a little point. That's an axis of rotation. If I rotate 180 degrees, where does this guy go? Down here. Where does this guy go? Up here. Each oxygen came onto another oxygen. So you see that there is a C2 axis down through, not in line with, but through the midpoint of the OO bond. Okay? So we've identified C2. I don't believe there's anything higher than that. No, not going to be, any C3s or anything like that. Okay? So, is there a perpendicular? Well, we looked at the possibility of anything being perpendicular, and so we've looked at all three of the, X, Y, Z directions or dimensions, right? So it doesn't really look like there's a perpendicular. One tricky axis to consider, though, is there's sometimes it would be perpendicular because this is coming out of the board, okay? So if I could rotate this molecule 180 degrees along that line, the H's wouldn't move. But in this case, the O's would move, right? It would reflect there or come over to here, okay? But sometimes there are some sneaky ways to get that perpendicular, because anything perpendicular. So if you came in here, actually, is there a perpendicular one this direction that we could rotate the H's onto each other? I don't think so, because anything that would bring the H's over, in that case, would put the O's here. So we'd have O's, O's, something like that, okay? So the O's are the problem here. So I don't see no perpendicular C2. So we're not going to the D side, in other words. Okay? So over here on the C side. So now we look for the horizontal mirror plane. Again, we're looking down the principal axis right now. So horizontal would be the plane of the board. So sigma H, yes, we do have a sigma H. The actual plane of the molecule, and again, it seems kind of weird, but yeah, the top half of an atom would reflect onto the bottom half, right? It would stay in its same position or be unmoved. So that defines symmetry. So we do have sigma H there. So this decides that this group is C2H. Okay? Why are you shaking your head?
It doesn't have a sigma H.
It doesn't have a sigma H?
No, I think.
It doesn't make sense.
I think instead of it just being, I think one of the hydrogens. I don't think the structure's right.
You don't think it's not flat?
No,
I think
it's not.
one of the hydrogens is protruding like out.
I think if you were to draw it again, one would be a dash, one would be a wedge. It's a bit weird.
They drew it with, okay, I didn't see that originally, you're right. The book has it drawn actually with both being wedged and coming out. And yeah, so if I had looked at that, then the sigma H would not be there, okay? Our C2 is still there, just to come back and reconfirm this, but there is no sigma perpendicular C2s then, okay? And then there is no sigma H, as we just said, so that corrects that, all right? And is there a sigma V? So a vertical mirror plane would have to contain this in it. So there's not really any way that we can reflect through a plane. Again, it looks like maybe the H's could reflect, but the O would end up in a different spot. Okay? And if you tried to make it this way, the H would end up there, the H would end up down there. Okay? If you did this, the O's don't line up on there. So it looks like there's no sigma V either. Okay? And so then we have to look for improper rotations. So we'd have to look for an S4. So if we rotate this 90 degrees, okay, that's going to put this over here, and immediately it's not going to line up with where another atom was, even if I'm then pushing it the other direction. So it looks like no S4. So this belongs in just the C2 point group, I believe. Now, again, this has a conformer. So if we had both hydrogens coming out of the board, if one of the hydrogens was into the board, behind the board, right, it would change, because then the C2 wouldn't even have been there. This only has a C2 because these are both out towards the board. So when we rotate it, but if this one was back away from the board, then you could think of it as being behind, right, the board. When we rotated it, this H is out in front of the board. They wouldn't line up that way. Okay? But then I think there might be another sneaky version of it there. Okay? All right. Just double checking that assignment was correct. This is one of the examples in the book here. Yes, they gave us the C2s. No. Okay. No. All right, yeah, so C2 is the correct assignment for this year. Okay. All right, let's look at our last one here. Hopefully you have all this. I'll go ahead and erase it just to create the space here for our 1,5 dibromonaphthalene. So axes of rotation here, again, borrowing from what we just learned here, I'm going to think, looking down on this molecule here, can I rotate it 180 degrees that way? It's really going to be the only rotation that's going to allow this bromine to end up on this bromine here. If I try the ones from the side, the top one's going to flip to the bottom's going to flip to the top. Okay? If I try one that's sort of flipping around left to right, the top one's going to end up over here in the top, bottom one's going to end up over there in the bottom. Okay? So it doesn't appear that there are any other C2s there. Okay? Yeah, other than that. Okay? Although this might be a sneaky C2 that I'm looking at right here. We're going to have to look at that carefully, because that would bring that there. That might be. So we got a C2. Okay. All right, what's our next question? Well, now we have to figure this out. Do we have a perpendicular C2 for this molecule or not? Okay. Okay. And I think that what I've drawn here is, yes, this is a perpendicular C2 axis. All right. It's quite tricky, without drawing this thing accurately to scale. But this bromine would flip over here onto this bromine. Okay. And maybe it doesn't go exactly. Actually, it might not go exactly through those points that I've drawn here, but I believe it's going to go through like that right there, which is going to allow this carbon to come to this carbon to go to not. No, it has to go through. It has to go through. Right, because of the odd numbers there. It has to go through like that. where I had it originally, which is going to allow this carbon to reflect to this carbon. Okay, it's going to allow these two to flip onto each other, these two to flip onto each other. This is going to reflect with this. Okay, and the bromine is going to rotate to this right here. All right, so it's one of the more difficult ones, but it is perpendicular to, again, to the C2 coming out of the board here. All right, so we have a C2, we have a perpendicular C2, so that moves us over to the D side. All right, then we have a horizontal mirror plane because these are benzenes, they're planar, right? So this whole molecule is flat. Horizontal, that plane is perpendicular to the axis of rotation, the main axis of rotation. So yes, we have a sigma H, and then that would give this the D2H assignment. Okay. Okay. Well, let's just wait. It's not right, though. It's a C2H. So I must not be quite right with my perpendicular axis here. To me, it looks like it's there, but sorry, it's not there. Okay? So forget about that. All right? Moral of this, right? Seeing me even struggle with it, it's not something you memorize. It's something you work hard at. All right? It's something you work hard at. Every single one of us. Myself included, all right? But there is huge benefit to doing this because, all right, so once this, by the way, this is not D2H, this is the C2H because the answer was no to the perpendiculars there, okay? Once you do it, once you get a molecule into a group, then the rest is not easy street, but you're going to see that it's a lot like, another molecule that we had earlier, or some other molecule you've looked at before. So let's some classic cases. Let's look at water here. We'll throw up a couple additional examples, right? So what's water have? Water has a C2 axis to it. All right, that's the highest axis of rotation that you're going to find. You're not going to find anything perpendicular to that. You can't rotate it 180 degrees from one of the sides or from the front or anything like that. So you got a C2. There are no perpendicular C2s. So you come over to the right side. Is there a vertical mirror plane? Yes. This, actually, I'll try to draw it here. This would be your sigma V. The left side would reflect on the right side through the oxygen. Okay? And so you have a sigma V that then terminates you at the C2V point group that you have there. Okay? Sorry. Okay. How about this one wasn't on the list. Let's look at BRF4. So bromine tetrafluoride, bromine normally, BRF5. Say it wasn't going to work out without a minus charge. Bromine has 7 valence electrons normally. 5 are being taken for bonds, and 1 is being left as a lone pair. So that's going to be the square pyramidal shape. Okay. Similar to the octahedral, but one of the bonds that would be down here has been replaced by a lone pair. Okay, so we call this square pyramidal. Okay. So if we look at this structure, the axis of rotation, the best axis of rotation is going to be the fluorine-bromine bond, that's in the axial position up there. And that's going to be a C4, right? Because you can rotate 90 degrees to bring it. There's also a C2 that's coincident with that. You can rotate it 180 degrees and bring each fluorine back onto a position. But we're looking for the highest value of n, so that's the smallest angle of rotation to bring the molecule back to itself. Okay? So there's our C4. All right? So we've got a C4 axis. Do we have any perpendicular C2 axes to it? So, perpendicular to that line would be, roughly through any one of these. But no, anytime you try to do that, the fluorine on the top would be reflected down to or rotated down to the bottom where the lone pair of electrons is. Okay, so there's no perpendicular C2s in this case. All right. Next, we would ask, do we have, so we're over here on the C side, do we have a horizontal mirror plane? Again, given our axis, we see it oriented here. We're thinking, do we have anything horizontal that we can reflect through? No, we don't, because again, that F would not end up where it is right now. So no horizontal mirror planes. Then we ask, do we have vertical mirror planes? Okay, and yes, we have several vertical mirror planes. We could bisect any one of the bonds. The board itself is a mirror plane. The back fluorines would reflect to the front. Okay, the plane coming straight out is a mirror plane, left to right. But also, each fluorine, bromine plane is a mirror plane, and the other two fluorines would reflect. So there's tons of vertical mirror planes on here. So yes, for sigma V's. So that tells us to go down here. Oops, sorry, that was yes, sigma V's. So we're at the C4V group for this bromine pentafluoride then. Okay? Follow along with how we do it? Okay. So this is, a fair amount of what your homework is going to be. I didn't get it posted in. I'll go right up to my office after class and post what your homework is. Let me just double check real quick because I may have a worksheet this time rather than... Yeah, well, there are a couple problems from the book, okay, and then a couple of molecules that I ask you to list the symmetry elements of. All right, now that's going to be the more frustrating part. I'll be honest. It's actually much harder to take a molecule and list all of the symmetry elements than it is to follow the flowchart. All right, the flowchart doesn't ask you to consider everything. It just lets you process your way to a point group, all right? But it is nevertheless very useful to be in good practice of finding symmetry elements in molecules. So I've given you a few molecules to consider in that regard, okay? Again, we're going to have a quiz next class on Chapter 3, okay? And then homework 4.1 will be due. We're going to do a lot more work on these what are called point groups and understanding what they are and how we can use them for various functions in chemistry. And we're going to get started with that next class. All right? Have a good rest of your day. I'll see you then.